Perfect. So thanks Mauricio for the nice introduction and welcome everyone to the talk. I'm very happy to see all of you. Of course, some of the faces I already know from past, so good to see you again. So I mean, as Mauricio said, we have been working I think more than 6, 7 years I guess now. So we have very productive collaborations, got like really world-class research outcome and open source contribution. So I'm looking forward to extending that to the next levels hopefully. With me after joining NYU. So a lot of work that I'm going to show you here is primarily the work done, I mean a lot of done work together in this collaboration effort, as well as my other team members from the TU Wien, where I still hold the group. So Alberto is still working and leading quite some projects there, as well as some of the new initiatives that I have done and started in NYU. In both campuses, in Tandon and as well as in Abu Dhabi. So my primary base is in Abu Dhabi, so I of course would welcome all of you there. So I'm part of 4 different centers, so there is quite some work that I'm going to show you which comes under the Center of Cybersecurity, the Center of Interactive Urban Cities, where we are looking into autonomous vehicles kind of systems, as well as the CARE Center, which is centered on AI and robotics. And now I'm like, recently joined the Center of Quantum Computing, where we are looking into the quantum machine learning, as well as the EDA problem, like the traditional EDA, which is my background earlier, to develop, for example, automated tools, design tools, and testing techniques for quantum circuits, So this is another great area where we're working together. So I think without delaying, I'll just proceed that, everyone knows that we are in a true era of now AI, and this is like going to stay there for long time, very very long time now. And the reasons I always give is that there is a certain rationale behind that why we are in this era. So if you look at this human history, that in the first age of mankind, the tribes who were having the highest manpower, most courageous, good skill set, they were ruling the nations, and the world. Later on, we entered into the age of resources and industry, where the richer nations are primarily which were having the natural fuels and all this thing. And I mean, everyone is well aware of the natural resource crisis nowadays, which is being faced worldwide, especially Europe is being hit very severely with that. And you can see that there is a lot of politics going in behind that. And a lot of times is, these countries who hold the natural resources or the industrial technology, strengths, they kind of control all this politics and stuff. So when we are moving towards the next stage, and we already have stepped quite much into that for the past like decade, I would say that people did not realize in the first 5 years, but now I think since the last 5 years, people are very much assured of this thing, that yes, we are in a new or transgressing into a new era, which is where the data is the new fuel. So whoever holds the power on the data, is ultimately, showing its strength and monopoly. And then innovation in technology is the new politics, and we have seen that, is, for example, if there are certain Chinese companies which have, done a high accelerated growth in certain technological evolution and in progress, and they are being banned, for example, in US, and then, things like that are happening. So having said that, getting the control on the technology, the new technology, the AI technology, is inevitable for everyone. So that's why there is a nationwide race in dominance or achieving a dominance in AI and machine learning pretty much everywhere. But on the other side, I'll show you that there is a wide range of applications where these technologies have already started proliferating, which means that it becomes kind of inevitable for us, without doing any progress in the machine learning on AI or any such aspect of data science, for example. So there is a smart prefix of pretty much in every system. Now we are talking about smart automobiles, smart grids, smart transportation systems, smart houses, smart cities. So it's like, in earlier times, when multi-core came, and now every processor is a by default multi-core. Today when we talk about ML, it may happen that in the next 5 years, every system by default has a machine learning component. So it would not be anything surprising. It's like, a basic requirement of any system to have some kind of intelligence to survive, or at least, function in unpredictable scenarios, or for the betterment of the humanity, or for improving the services for us, or things like that. So you'll see that there is a wide range of, like also smart healthcare. This is a big area where people are working into this. So the bottom line is that we are integrating trillions of sensors into these things. On the one side, even an isolated system is super complex, but imagine that when these systems are being connected together in a Internet of Things kind of stuff. Now it's an Internet of Smart Things or Internet of Smart Cyber Physical Things. Imagine whatever combination that you can think of, you'll see that you need to somehow derive valuable knowledge from this data that these trillions of sensors are generating. And you want these systems to function, optimize over the period of time as well. So AI in general, like is a very, very big umbrella, but the modern technologies that we are using is primarily machine learning or deep learning technologies. They are inevitable for us at the moment, because we want to effectively infer the knowledge, derive short term and long term predictions, and then move forward with the problems that these systems are facing when they are subjected to these unpredictable scenarios. Now, of course, whenever we think about designing such systems, the first and foremost challenge for us is always the performance and energy efficiency. So, no question about that. So, and when we talk about anyway TinyML or EdgeAI, we all know that, I mean, of course, performance per power efficiency is the ultimate design objective that you want to achieve. But you will see that many of these applications that I have shown you here, many of them are actually critical applications in one or the other form. I mean, they can be life threatening to all the way up to soft critical, what I say is like, which means that you still cannot afford something happening with those systems, violating, so things like this. Now, the nature of the catastrophe can vary, of course, depending upon the application, but healthcare applications, you don't want those systems to go, malfunctioning more. Same with the smart industries, same with the smart houses, name anything. I mean, so it's not like much of entertainment anymore, which was earlier generation, was the most challenging application. All these applications require some form of robustness. Now, robustness has a very diverse kind of facets. When you look into the system design principle, it can go into different types of reliability and dependability requirements to all the way up to security and privacy. And privacy of data and security of data has become even more important in these machine learning systems, because there are new attack surfaces, and I'll show you that you can even hack into these systems without even opening the system. So you can do a plain black box model attacks, and it's because the AI model itself or machine learning model itself is a black box model. So it's a transfer function of an input and output relationship. So I can, if I can tap into the input and output of such a system, I can actually build a proxy system easily, which will be kind of approximately equal or can be sometimes very, very close to that. So when we talk about TinyML and EdgeAI, these are the two communities which, for example, started with different set of applications, but then there is some kind of overlap which is being formed, and I'll talk about those synergies and those commonalities between them. But originally their target applications were very, very different. So, but when we do really critically look at those or scrutinize the requirements, you will see that they follow similar design principles. Effectively, I have a very, very complex model, and I need to fit and map this model to a very small device. Now, that small device can be either your mobile phone, can be an electronic control unit in a car, can be a very, very, very tiny sensor deployed in a forest or anywhere else. So, if I want to design such a system, or you guys want to design such a system today or tomorrow, then you need a set of expertise to do that. The first expertise, for example, let me get my the stuff. So first expertise, for example, you need to know the ML algorithms. It's not like a time where we were just designing chips and we didn't care about the set of applications. We only care about the data flows and control flows or abstract task graphs. But now we exactly need to know the precise properties or even design principles of these ML algorithms. If you don't know the structure of recurrent network or a deep neural network, convolutional network, then designing an efficient accelerator is a very tough job for you. Similarly, then you need to know the hardware design principles, and now in the system ML community, you do hardware aware ML algorithm design and you ML aware hardware design. So let's say if you have to design a neural processing unit, and you know that I'm quantizing this neural network for 4 bits, I can have a 4-bit MAC unit. Vice versa, you can have 4-bit MAC units and then train your network to be fit to the 4-bit kind of stuff also. And then this is like an application, and this is like your actual processing hardware, but there is a lot of system software stack in between and lot of critical constraints that comes from the application. So that's when the embedded system design knowledge is also important there. So you will see that all that you traditionally were studying, from data flow systems, data flow optimizations, synchronous data flow graphs, to all the way up to system level design principles to embrace multi-objective optimizations, they are back into the story with these kind of systems. Now many of these systems of course are battery operated devices, so you need to be very careful about the energy. Qualcomm for example is working on always on use cases, so you have like smart sensors which are always on, so you need to be careful about that. And there is also this concept of zero power devices, which mean that whatever energy that you harvest or power you harvest, that's the budget that you can spend. So net would be zero, which means that you don't need to power those kind of devices for that. Now going a bit into the numbers, so you can see is that what we have is here the traditional one, this cloud AI kind of stuff, and rest is like this. So if you look at the landscape of the systems, pretty much 80 to 90% of the real world systems are embedded systems or cyber physical systems, you know. So you see that the applications of EdgeAI and TinyML is like 80 to 90% of the total computing devices that we are talking about. So how many percent of the people will be working here? So you see that mostly enterprises. So even if you get an expert of that, you know, you just go and join Google, Amazon, Microsoft, you know, or Meta for example. But the rest is all gone from your hand primarily, or clinical AI kind of stuff. But so those kind of things are working on very, very high-end GPU systems like A100 or next H100 for example, which is coming now. And then we are talking about terabytes of memory and then they're used for model training and stuff. So on the other side, if you look at we as embedded system designer and stuff, so we look into the systems which are constrained with either with memory or extremely constrained with the memory, and you can see it here that there are tight constraints to all the way to extreme constraints, and then we need to design those systems for fitting those constraints. Now I'll show you with the help of one design flow that primarily the optimizations that we perform are kind of very similar. Like I want to do a network compression, I want to do a neural architectural search, I want to do quantization and those kind of stuff. So they are very similar. So if you want to do it for EdgeAI or TinyML, the main methodology may remain similar, but the constraint actually is very tightened, which means the potential number of solutions that your design space exploration can find will actually be either very small space or a little bit bigger space. Now TinyML started with the microcontrollers and extending that with some acceleration where they worked into compiler tool chains to support some ML kind of operations. But now I think there is a consensus that we need a neural accelerator if we want to accelerate them. So that's why every company is building their own neural accelerators. In TinyML you may have a neural accelerator NPU of 4x4 array, but for EdgeAI you maybe have like something 256 by 256 array or 128 by 128. You can see is that the sizing you can dimension the problem accordingly. Now let's a little bit have a quantitative look on different design challenges before we proceed to some of the solutions. So I think everyone knows that deeper we are making the network, more complex it is getting. So this graph only shows one aspect of the complexity, and that's in terms of, for example, the operations that you have to perform versus the accuracy. And you can see is that these networks which are becoming more and more accurate are also becoming complex. But it doesn't mean that this network, for example, which is slightly less complex compared to that, is consuming less time, because the execution time is a very different property, and this highly depends upon your memory access patterns. So it may happen that you are accessing a memory in a relatively better way in this network compared to this one than the other network, which apparently looks smaller compared to the number of weights, like how many million weights, but effectively that the control flow is so complex, the data flow is so complex that you have to go back and forth. There is a lot of internal dependency, and then you kind of are stuck with a lot of the memory access problems in those cases. So I'll skip through that. Of course, I mean I will give you these slides. You can go through in the details of that. But just to show you this slide from Microsoft, that what happened is over the period of time they are moving into more and more complex networks. For example, Megatron was 2,000 times, more than 2,000 times more complex than less than 50, and the GPT-3, and these are all the natural language processing algorithms. They were like 90,000 more complex compared to that. Now, some years ago when I was showing this slide, some people told me, yeah, but you are talking about a visual network versus an NLP, and NLP, I mean, how do you put in embedded? I mean, you still want some embedded NLP, I mean. But before going to this discussion, look at the now current trend of even the visual stuff. People are talking about visual transformers, like vision transformers or coat nets, They are based on these attention principles, and they are also super complex, So if you want to build a dedicated accelerator for that, maybe the regular NPU is not suitable. So if you look at the H100, the new GPU which is coming up, it has a neural tensor cores to accelerate your neural processors, but it has a dedicated tensor transformer engine to accelerate your transformer flows, So designing a specialized hardware accelerator for transformers is great, but transformers algorithm also evolve over the period of time. So you need some kind of like configurable hardware, and that's one of the topics that I would be offering later on. So the challenging question that, I mean, if we keep on following this trend, how we can ensure that we can have still valuable or efficient embedded implementations of that targeting the edge applications. Now on the other hand, we talk about efficiency as well. A lot of time these people talk about that, okay, we can beat humans for certain specialized tasks, but if your algorithm runs on a big cloud and a big data center and things like that, then they are consuming like megawatts of powers we are talking about, but our brain only works at 20 watts or less. So how can we ensure that this comparison is fair? So if I'll talk about robomorphic computing later on, but if I want to put a small brain inside my robot, then this has to function pretty much in a very, very low power energy, because I cannot keep on feeding very high power or megawatt plug into that. So, and that if in subjected to the online learning scenarios, then which means they are learning like humans are learning. So that's a futuristic scenario, but imagine we are moving towards there in next 10 years to 20 years. So we need to work now for that. So how can you enable efficient real-time learning at extremely low power budgets? That's the holy grail question nowadays that the embedded machine learning community is striving for. Now, just to give you a very quick glimpses, this is TPU's version 3 supercomputer. This was the earlier, earlier version of Selene, which was, I mean, you can just see they are consuming a huge amount of power. And then, there were also some studies where people talked about that if you are training your machine learning algorithms on these clouds or these supercomputers, then they are like, consuming a lot of power and have a very bad carbon footprint, for example, and they're worse than, for example, multiple cars that we are talking. I mean, we are always cursing the automobile industry or flight industry, but nobody is talking about the training industry. ML training industry is also, creating a lot of carbon footprint. So there was then a follow paper at Nature Machine Learning, which actually then studied many different other algorithms for the carbon footprint also. So Cerebrus actually was a groundbreaking concept which gave the world's first wafer scale chip. That's one of the first chips which was one chip per wafer, and earlier people were not having because of the yield issues, and they cannot still have like the other, for example, superscale processor like kind of stuff in single wafer single chip because of yield issues. But since they have a very regularized neural accelerator array, they were able to for example fabricate many these tiles, and then even if some PEs are faulty, then you can kind of hide them and then start still using the next one. So the biggest challenge is in the tool to embrace the variability and testing and fault kind of stuff. So you can see here that the Cerebrus biggest chip is like this, and at that time the largest GPU was that. So, but the good thing is that this only requires 20 kilowatts versus 1 megawatt you can already compare. So this can accelerate the training by reducing, of course, lot of inter-chip communication power and other kind of stuff and things. So this is amazing in one sense. And of course, by technology scaling, they are now doubling up all the number of Ps and AI cores, and they are producing better and better chips kind of stuff. But still, I mean, this is like we are not putting a big wafer chip on a small sensor node. So this is not the TinyML EdgeAI. I just want to give you a glimpse that where the training side is also going, and there's a lot of work going on, accelerator training or efficient training, also things. Now there are different cross-layer design flows which are talking about optimizing your systems for TinyML or EdgeAI. There are ARM tool chains for that. There's micro-TVM, there's TensorFlow Lite, and things like this. So one of my students has used TensorFlow Lite to develop some things for mobile apps also. So then there are the specialized hardware accelerators, which are, for example, doing these matrix multiplications, vector multiplications and things like this. And then there is a specialized DNN optimizations like neural architectural search, which is aware of the underlying hardware constraints. So there are two different schools of thoughts to develop machine learning algorithms. One is where you have some kind of model configuration manually given certain set of configurations, and then you do hyperparameter tuning and then train that model, and people do that also, even still today in modern days they do that. Or the other way is the neural architecture search, where you define an optimization problem, you give your set of constraints and a design goal, and your optimization algorithm automatically finds a DNN architecture. How many layers, what should come into one layer, how the layers connection should look like, and then while doing the hyperparameter tuning inside that. This is super complex. If you need, for example, just to give you an idea, if you need, for example, 1 month to design a neural network using, for example, one set of resource, for a regular method you may need, for example, 6 months for designing using a NAS, because NAS, when you solve a multi-objective optimization problem, it's a combinatorial explosion of the combinations, and then you can already see that this is a very, very time consuming job. So accelerating NAS is another great area to work on, and people are looking into this thing, but again this is something which is like very ongoing kind of research. Then pruning and quantization, I mean, I'll go into details of this slightly, are the great methods to compress them. So now one of the issues with these kind of systems is that they're primarily targeting performance, and then of course implicitly putting the models inside for the energy efficiency also, but they are very lightweight models. The reason is that when you have to optimize and compress a network and evaluate a certain candidate solution, you need analytical models. So analytical models depend upon your actual hardware platform and things like that. So but what about security, what about reliability and safety? How do you put those kind of requirements inside those things? So for example, Alberto has recently published a work where he integrated the security into energy efficient NAS flow, which was another previous work that we did for stuff. So this kind of stuff. So now security I was talking about, that is a kind of a very complex problem that the machine learning community faces. It's in earlier times when we talk about any regular system, the first thing is always access control. So if I am unable to gain an access control, doing a security attack on my system is very, very complex. So a lot of time with access control, people can already do intrusion detection kind of stuff and anomaly detection kind of things, and it's done. But with the machine learning, robustness is such a super complex problem that I can do a security attack without entering into the system. I can do a security attack by perturbing the environment, and you will just not realize that. But on the other side, this whole security loopholes also disclosed that these machine learning algorithms lack robustness, which means that if there is a deviation in the distribution of your actual real world data compared to your training data set distribution, then your machine learning algorithm will also fail again. This is traditionally called a domain shift problem, and this is very complex problem which people have faced, or especially now facing in the healthcare data sets, where you may have for one class lot of data samples, but for the other class you may have very less data samples, or the data samples of one class deviate when you face in the real time kind of stuff. So people are looking into interesting ideas like self-supervised learning, contrastive learning to cope that. But in general, if you look at this, there is still another kind of robustness issues. So I show you two videos here. There is a Chinese company, they bought one of the Tesla cars, and what they did is black box experiments. They generated some kind of random noise, showed it to the car, and then the weather control system was activated and the wipers were already working, you can see here. Similarly, what they have done, they put 3 white patches on the road, and then when they activated the autopilot, the car thought that, oh, there is a lane change, and then it immediately changed the lane. So if you look at this is what happened with the car, that as soon as he activated the autopilot, this kind of quickly moved that. So these kind of studies are already available, but this already shows that how dangerous these kind of systems can be. But for any testing guy, this would also raise a question that how do you verify your machine learning algorithms, So the formal analysis and verification is also is a very important topic for these kind of systems, but it's very complex because this system is stochastic kind of systems, and we all know that for the comprehensive formal verification of such kind of system is again a very is kind of ill posed problem. So it's very difficult to solve it comprehensively. So summarizing the challenges, I mean, of course there are a lot of other challenges I did not dive into. They are related to the reliability kind of stuff. For example, you can have permanent faults on the neural accelerators, you can have soft errors. So we did these works also in an industrial project. I can talk about that after the talk offline, because of the IP stuff in general. But I can tell you that a lot of these things, for example, they are very functional and very helpful for the safety critical systems. I'll give you a little bit overview of the different type of security threats, like during the training and during the inference time, and I'll put a bit more focus on what kind of techniques are required for memory optimization and compute engines. So that's the first part where I have design challenges introduced. Any question until now before I move to the next part? Are the challenges clear? Do they excite you that these are the real challenges and are significant challenges where we need to take some actions? Any yes, no? Okay, so I assume that. So typically I like to have interactive talks, but here because of the time and recording we can go one directional communication. So in general I believe that there is no single silver bullet to address these challenges. So we need to look from these problems from a very multi-dimensional kind of aspects. So in the lab, so I have a lab which is called KTech in Vienna, and the eBrain lab is the name of my lab in New York, Abu Dhabi campus. So we are looking into this as a multi-dimensional research challenge. So we are first studying these problems on regular GPUs, understanding their complexities. We are also porting them on embedded GPUs and try to build analytical models of them. We are looking into like dedicated pipelines for these neural processing units, specialized on-chip memory architectures, as well as approximate computing. This is again a great area where we can reduce energy consumption using approximating, but approximating neural networks is a complex problem. Again, unlike the regular image processing, the reason is that because if you touch any sensitive neuron and approximate that, it can destroy your whole accuracy. But there are numerous numbers of non-sensitive neurons where you can approximate significantly. So that has to be done judiciously, so this is where you have to be very careful. So we are looking into the hardware software co-design problems, automated optimization tools where, for example, you give me a deep neural network, you give me a platform, and then somehow this tool compresses and then outputs something. So to build such kind of tools, we do a lot of research into, for example, number formats, specialized quantization techniques, specialized pruning methods, and I'll talk about what is the pruning and quantization in a while. And then we put them, for example, either separately in a flow, or we can also do them in a neural architectural search. So we are also looking into the next generation neuromorphic architectures, for example, Intel Lohi chip, which is an asynchronous chip for accelerating the spiking neural networks. And spiking neural networks are considered as the third generation of the neural networks, and they are biologically more plausible because their model is much closer to our understanding of how the neuron works as compared to an artificial neuron that we use in deep neural networks. So Alberto is also leading together with, also we are working quite heavily with Mauricio on and Guido on these joint projects with working on the Lohi chip, and we have access to that, and we have very interesting works going on in that area as well. And then one of my students started working on building up the crossbar arrays, but this is little bit going a little low because many of the models have some inaccuracies. So we are waiting until this technology gets mature, and then how to build up the system, then we can do that. And of course 3D stacking is where you will need all these kind of systems to put together and get the best out of everything. So just to give you an idea that how does this actually function, you can see that this is like a diagram, architectural diagram of Intel TPU, the first generation of that. It was a 64K, for example, per cycle MAC operations, because it's a 256 by 256 array. You can see that then they have accumulated activation functions, which are typically the subsequent layers after any convolutional block that you will process. They have a dedicated FIFO for the weights. The data is then passed through across different layer functioning or layer operations, and for that you need some local storage, and you also need some kind of data arrangement unit, because once you feed the data back for the next layer processing or within bigger convolution within one single layer, even then you need to rearrange the data in different ways. So then this control is the real IP, how do you control all these kind of stuff. The good thing about this thing is that this is a PCI Express based kind of accelerator. You don't need to couple it with a like a host CPU, like just like with a bus or something. So you can do a plug and play with these kind of cards. So they are really extensible in many things. The alternate architecture is that you build such kind of neural architecture and a memory, and then couple it with a bus and a RISC-V core, for example. So that's like a multi-process system on chip kind of architecture, and these are also available. Now, how do you map your algorithm on them? This is like there are different data flow techniques, mapping techniques for this. One of them, which is very common and easily usable for dense networks, is called weight stationary model, which means that I have these weight matrices, and I can map those weight matrices on these PEs like that, and then I can stream the data input cycle by cycle into that, and then what I do is that this multiplied by this goes next, plus this multiplied by this goes next, plus, so at the end what you get is the sum of these products, and that's the basic element of any convolutional block that you are doing. So that's how at the end of this thing you will get one of the sum of products or the partial outputs, and you will feed it back, and then in things you will have multiple channels which are being processed in this case. You can see that that's how the data is processed and where it stays there stationary, So in general, this offers you a lot of energy savings, and now the trick is that can I have a weight reuse, can I have the intermediate feature map reuse and things like this. So if you have a good reuse policies, then you can save a lot of energy transfer from the memory accesses as well also. So what I'll give you a little bit detailed overview of the full flow that we have, and I'm not going to dive into the methods. We can just talk this offline so that you get the bigger picture. The first thing what we do is that besides accelerator training, we are looking into some of the techniques for accelerating the training, but what we do mostly at the training side is study the backdoor anomalies kind of stuff. So when you are training your neural network, you don't need to read that, that's a very tiny stuff. You will get the slides and you can zoom at screen. I'm just gonna give you a bigger picture. So when you train your thing, you need a cloud effectively to train that, okay. So the fast training is a separate topic, but when you're training on a cloud, that cloud is a third party service. So you also train on third party data even sometimes, which is not from you. So someone can either poison that data, or the cloud service provider can itself poison the data or manipulate with your models. These are called backdoor attacks or data poisoning attacks, and they can feed, for example, some special noise and train your network for that special noise. When you show it in the real world, the network will malfunction, but for your input it will function correctly. So you will never be able to realize that my network has some backdoor inside that anybody else can feel, for example, tap in future when it's deployed in the real world. So those kind of problems are very, very complex. So again, it's a complex mathematical problem. You have to think about what is the feature space, how orthogonal is the feature space, how separable are the features. So those kind of stuff. I have a postdoc dedicatedly working in this area, and then we are trying to understand what are the vulnerabilities to backdoors, and if we can close those vulnerabilities and ensure that we can still have some kind of robust learning. Now you can get a pre-trained model, you can retrain that model, and then you can compress it using pruning and quantization. Or what we can do is that we can also do some kind of the neural architectural search that you can see here and generate that. So the second thing, for example, what we do is that we also do memory optimizations for the reuse policies. I'll just give you some numbers. So one of the pruning methods that we have developed can actually prune your system up to 190x. Depending upon the model, the potential is more or less. So we can prune from 50x to 190x and memory reductions with very, very minimal loss. This is one of the first works that we have done jointly. Then there is also a complete project going on approximation. I told you that you can approximate neural networks, but at some point the approximations can be critical. So there is a growing concept of self-healing approximations or curable approximations, and we are the first ones to propose very pioneer work in this area, where you can generate the approximate modules which can heal from their errors. For example, if you are doing multiply accumulate, if the multiply generate for a particular input scenario -2 error, and in the next case it generates a +2 error. So once you do accumulation phase, your net error is 0. So they can heal back from this thing. So these are called like reflexive multipliers or mirror multiplier designs. So and similarly you can do it also with the adders also. And in some cases, since it's a kind of the distribution cannot be perfect in all scenarios, if the distribution is slightly deviant, the input distribution is slightly deviant, where you will have some errors. So we have a one consolidated error control, correction control at the end of the accelerator. So we don't need to correct error in each and every block. We just can stochastically correct most of the error at the end of the block. So there is a consolidated error correction work that we have also done that. So we have shown in this particular work we can add 1.5x energy saving with no accuracy loss and things like this. Similarly, there is a lot of work that one of my PhD students is only working on the memory stuff. So we have done off-chip optimizations as well as on-chip optimizations. Then we had an industrial project where we basically were given the job that if we get a network, like pre-trained network that we can retrain for our application, how we can robustify this against soft errors first of all, and second is that how we can embrace the permanent faults to increase the yield for that company. So for example, if they are building up some neural accelerators, they wanted to increase the yield of that. And the state of the art at that time was that you can do fault aware training. For example, you get the fault map of that chip and retrain your network, but retraining is very costly. If I am producing millions of chips, I cannot do a retraining for 1 million chips. So we actually developed an automated tool which can do a efficient mapping considering the fault maps of that, and this is like in basically no time, and we can only do the partial retraining where required, for example, to further increase the yield in the second phase, and that's also great work. And then for the soft errors, for example, we have proposed some kind of checker blocks which are range restriction blocks, and what they can do is that they can bound the your output of your activation function and figure it out from the activation function's output that if some aggressive fault has happened or not, and if this is within bound, then we can still ensure that our final selection of the final class is still highly probable to the actual correct case. So those kind of things that we can already show. Then we went one step up. Then okay, if we are generating such kind of systems, can I formally give you some guarantees? So we started looking into the noise tolerance of a network. For any given noise pattern, can I give you the bounds formally? So there is one PhD student working in Vienna exactly on those kind of stuff. So she's looking into model checkers, deriving those bounds, and then looking into the noise tolerance of these kind of stuff. And then there we also studied into that how we can systematically unbias a network, if we are, because a lot of tolerance problems comes from the unbiasing and as well as also the bad distribution of the class samples and things like this. Now when we are deploying this energy efficient and reliable stuff, there is still a security attack that can happen at the deployment phase, just like I showed you for the Tesla car, where you can buy a system and you can attack. This is called adversarial attack, which is done at the inference time. So there are a lot of attacks which can be done. So one type of attack which is done by accessing the system, this is possible. Even learning the inside IP through a proxy attack, and generating a proxy white box model and then doing a much more powerful attack, which is invisible to even if you have multi-tier. Let's say you have a look at the screen and you cannot even see the difference between the noisy image and the actual image. Or you can do the environmental perturbations. For example, if there is a autonomous parking going to happen in this area, I can paint some artistic stuff on the wall, and then somehow this pattern will mislead your IP. And how did I learn that? This is again a black box kind of stuff, by solving an optimization problem. These are decision based attacks where you only know the final decision of the system to identify a noise which can move a sample from one class to the other class. So those are typically the samples along the boundary kind of stuff. And similarly we are looking into many of these kind of issues which are ongoing in this stuff. So just to give you an idea, skip through that, I show you some of the results that what's the potential of the pruning. Of course, this is done systematically. So if you have, for example, 1 million neurons in your neural network, I can tell you that maybe 90% of those neurons are really not important for that particular task for which you are retraining. Okay, so I can kick out those neurons and retrain your network with only the remaining 10% of the neurons. So you can see is that, so one of my students, Abdullah, has done these experiments. So we started with this thing and then we can compress it up to 90-95%. We have these experiments for many different networks. I'm just not showing you all the slides, so just a very simple one, because everyone knows what is LeNet and what is MNIST in the machine learning. So we took a very basic example here for to explain. So you can see that this D is 95% pruned and retrained, and this is the network that I need to work for that. Then we do the quantization. So typically when you train a network, your each weight is a 32-bit floating point value. So when you do a multiply, so weight with an input, you're doing a 32-bit floating point multiplication, which is very costly. So one thing you can do, you can convert to 32-bit fixed point, or you can even convert it to 16-bit fixed point, or you can even do it, for example, 8-bit or 4-bit or even 2-bit or 1-bit, those binary networks, so you can do that even. So we have done that for all these pool networks, and you can see that the D1, which is nice, let's say orange, this line, kind of a yellowish line, you can see that we can go up to 5-bit. Of course 5-bit is strange to represent in registers, so we can adopt an 8-bit for that. And in some cases, which for example this B, even the 4-bit is good enough. So there is very interesting work from IBM where they have looked into different bit widths used for the quantization of different layers. So you don't need even the same bit width for all the layers. You can actually do a non-linear quantization as well as different type of hybrid quantization for for one network, and this is again a great area to explore, because this again is a design space exploration problem. And then which type of bit width, which data format, how many neurons, that's again a challenging problem that has to be solved. So people are now trying to put this pruning and quantization even in the LAS flow so that they can generate a compact model automatically look into that. Okay. Then next stage that you can do is the hardware approximation. You can further approximate those multipliers to get another 20% of energy saving. So you get like a lot of energy savings from optimizing the algorithm again. That's why we started from hardware, went into the tools and software optimizations, because this is where you get the maximum of the savings, and then now you can design your special hardware for a highly quantized and sparse network, and then hopefully look into that. And now we can also do this even in a structured way, so that even a dense accelerator can be used even for the structured pool networks also. So I skip that, and these are like some of the pipelines that we are developing. I skip this thing. These memory optimizations, just to give you an idea that we can identify the reuse across many different things like weights, input, intermediate feature maps, output feature maps, and then we can optimize data. But we also do automated tool of optimal mapping of your data into the DRAM based on the DRAM structure. It's a banked DRAM configuration working at the moment, or is it a sub array level parallelism like SALF kind of configuration working on, or is there anything like single bank kind of configuration? So based on that, you can actually define an optimal policy of mapping the data, considering your of course neural architectural array, so that you know that in which way I will feed the data to minimize the transfers between my on chip and off chip memory. And this can lead up to 96% of the EDP savings in this case, we can tell. So one of the works that that primarily this is done at Theo's lab, and we are also doing it in our lab these days, is like that we don't need a lot of optimizations only at the hardware or software level, but we can also play with the design of the application. Like if I am, for example, going to do an object detection, do I need the same computing effort for each and every part of the image? Maybe not. So for example, one technique is like resizing. I can shrink the size, but by resizing I can blur some features which can lead to inaccurate object detection, or skipping some cases. Or there is one approach, for example, which is introduced originally by Theo, one of my again nice friends with in Cyprus, which is called selective tiled partitioning. So we are looking into actually some principles that we learned, for example, my background in video processing, where we can do some kind of heterogeneous tiling as well as region of interest identification, and then do some more aggressive machine learning on those parts, and for the rest of the parts you can have very, very lightweight. So you can do a computational scaling with these kind of stuff. Again, now I think this is most of the design principles are this what we are doing, but now we are applying these design principles to many different type of networks, and they have all unique properties, so that's why we have unique results for that. So one is of course convolutional neural network, but for example Alberto led a big project on convolutional neural networks, so with many students from Torino, mostly this is a great outcome of this thing. We proposed one of the world's first quantization framework for the capsule networks. We also proposed one of the world's first accelerated training network for capsule networks. We also proposed one of the world's first neural architecture search frameworks. These are the three first open source contributions which are done in this area, and these are like then now are getting up the attention of the community, and then again the machine learning community. We are not traditionally from machine learning community, so if they are getting we are getting their attention, this is already amazing. I think Alberto was invited by some of the ICML and other folks also for some workshops and dedicated talks, which is a great achievement for for a student, and I'm very happy for that. So I think this is an amazing outcome. We starting from a different backgrounds, getting into this field and having these achievements. And the good thing, they are open source. So of course, I mean, we are not a company, so these open source you cannot expect at professional level, but we are trying to make them more and more mature over the period of time, and hopefully at some point in time they will be in a very good situation. So again, I mean, I just skip through these parts. We are doing a lot of effort on optimizing the systems and applications, spiking neural networks for these things. And now my ultimate goal is that if we can build up a autonomous driving use case using a spiking neural network as well as the neuromorphic accelerator. Now it can be a Lohi processor, but it can be our own custom built SNN accelerator. We will see that because of just the access to the hardware is very restricted. So we are currently thinking that I mean, I really personally want to build our own neural accelerator so that we just get more freedom to work into this kind of stuff, and now with NYU AD we can even fabricate that chip. So this is great. We have funds, we have resources, we have access to the fab, so that's amazing thing. And at the end I want to demonstrate that if we are deploying these kind of neuromorphic stuff in autonomous vehicle use cases, and especially due to their unsupervised learning capabilities of SNNs, can be function very well in the real time learning scenarios. That would be a great use case to compare in the next 2 to 3 years. I think this will be a great milestone to achieve also. Again, spiking networks, there is another student working on optimizing this for learning methods, energy efficiency, reliability and security, and again the quantization of these things. So I skip through those parts. In the security, I mean, if you look at this in most of the cyber physical systems, originally start from the recommendation systems, but now the machine learning is heavily proliferated into decision making bodies also, not only in healthcare but also in the autonomous vehicles or mobile robots use cases also. So there is a DL slam, there is like DL based depth estimation, odometry, there is a decision making based on, for example, lane changing like what I showed you and things like that. So in these kind of cases, when you deploy deep neural networks, you can do these attacks, and I showed you this here. For example, in stop sign you can add a very invisible noise, you cannot see a difference between them, and then it's not a stop sign, it's rather says 60 km limit or turn right or turn left. Similarly here what you can see is that this they generated custom glasses, and if you just put them on your eyes, then this lady can, for example, be seen as someone else. So these are called impersonation attacks. So we have done a lot of these kind of attacks, and currently we are looking into learning environmental patches which can actually fool in a full environment, in like simulators like Carla or Gazebo, or even when deployed on, for example, the real robots Husky in the labs, how you can really manipulate them, because it's not about really access, it's about driver's attention also. So lot of time, even, I mean, like these are like tough attacks to do, but even I can put a patch which looks like very normal, like how do you know that on this box there is nothing printed that can fool my AI algorithm? It's so difficult because it will never get my attention. I'm looking at first time this world of IEEE with lot of logos, and I don't know, there is a small patch, a pattern which is inserted there which can, for example, immediately fool my, let's assume I'm wearing a Google glasses or any smart glasses, and then they can fool that. So those kind of stuff that you can do. Another biggest issue is the privacy of these IPs, because we are generating millions of dollars, we are spending millions of dollars to generate that IP. Now I just buy that system in $200, let's say, or $2,000, and I can then re-engineering or reverse engineering that IP through IP stealing attacks. So you need to preserve that IP. That's the first thing, monetary benefits. But other thing is that people have done that if they can steal your model, they can actually backtrack and find the data which was used to build that model. And because your model is the representation of your data, it's as good as your data. So which means that preservation of the of your model is extremely important, and that's why there is a completely new era of privacy preserving ML, where you actually learn on encrypted data, for example using homomorphic encryption, okay, or you do some other kind of encryption and then decryption and things like that. So a lot of those kind of things are important. So we are running 3 big projects in these 3 different areas also. Let's skip through that. We have also, of course, security of SNN. For example, I think we did one of the first attacks on the DVS cameras, which is again a camera, it's a dynamic vision sensor which can only sense the images in forms of spikes. So it's a gradient change that we record. So this is one of the first one, which is published at IROS, which is a robotic conference, and we show that if these kind of cameras are deployed in robotic prototypes, how easy they can be hacked, and you can do these attacks for them. So at NYU AD, what we did is that we basically tried to develop another very nice application. This is where there's a lot of medical imaging going on. So a lot of time this medical imaging is done at clinical AI. You need big servers in hospitals to do that. Now imagine that we have some health center in some undeveloped area in third world countries and stuff, and majority of the countries are there, like for example in subcontinent, Pakistan, India, Sri Lanka, Bangladesh, all that region of South Asia, even lot of Asian countries, lot of the African countries and other places, even the South American ones. So a lot of times you may not have access to those resources, first of all, in those remote areas where, let's say, villages or towns and stuff. Other thing is that your physician can be traveling, so you are decoupling him. So at that time maybe the internet access is not good or something else happens. So we are enabling a very small, let's say you take the Intel compute stick or some other accelerator kind of like off the shelf component, and then you accelerate all this medical imaging on that. So this is again a very complex problem, because medical image processing using deep learning is again a super complex algorithm. So we, for example, started with all-in-one framework, and now we are customizing that, and one of my students has developed a framework which is on top of the all-in-one from MIT, and now he is like, looking into, and we are extending that. So we are hoping that we can build up this framework, which is an automated framework. I have a project for 1 year for this, where we first we are working in X-rays, but then we will extend it for ultrasound images or MRIs, and then you can do on your mobile device or an NPU or an embedded GPU or anything what you want. You give us that platform and we can automatically output to the network, which can run there in real time doing this processing. Another great application of this machine learning is this handheld ultrasound device that we are developing in my team in TU Wien, together with a EU project which is done with the Philips Healthcare. So our part is basically developing a deep neural network which can for example do the segmentation of the ultrasound images, extract for example your current fetus and later on the baby state, and then also can monitor that if the movements are correct, and then do some short-term predictions that if this is growing in right direction or not. And there are studies and requirements from the Philips Healthcare that they gave that for example a lot of miscarriages happen in early stages because of this thing, that not proper monitoring is happening, or ladies are a bit hesitant or shy or things like this. And especially again I feel a great need for this in the third world countries where those societal issues and challenges are also there, so people can have this in their home and then can do this self monitoring, and then if something happens it will give you an indication that now you can go to a doctor and then do the checkup rather than only going in the last stages. So we did for example also a very nice neural architecture framework for customized network optimizations for healthcare applications. So I should show you another thing. So my another goal that I started in NYU AD was that in modern developed countries you have vehicles with advanced features, but if you go to a lot of not developed properly countries, then they have automotives with basically no safety features and stuff, okay? And a lot of time those drivers are like driving not as per the rules and stuff, so they need some indications where they can save themselves. There are a lot of accidents happening there. Even I have seen in my city that a lot of accident happens when people are driving on motorway and suddenly go to sleep. This is a very common problem, and also sometimes accidents just happen because someone is just putting a brake very quickly and you are just looking towards your kid or someone else talking and looking at mobile phone. Nobody cares about those restrictions, So for those things we are building up a solution which is out of the box and does not need any tapping into your car and automobile, no safety certification stuff, because we are not entering into the control of automotive, we are giving assistance to the drivers. So this kind of application develops, for example, and also a lot of, like, even in my city there is a lot of fog. My father always tells me that I have such a trouble in driving in a fog, and the fog can be so dense that after 2 feet you cannot see anything, that's the problem. So we started working in this last year, and I have now 2 more students who will continue that work. You can see is that, so this is kind of a network which can do object detection, but also lane detection and some other detections kind of stuff using the mobile phones. And there are a lot of challenges, because if you just change out different mobile phones, your device changes. So your network should be portable, scalable to the network device, to the mobile device. Plus the cameras change, which means your network should be robust, trained. Second, we don't have access to those real world data sets, which means it has to be trained in a way that it is generic in a nature. So it's all complex problem, domain shift problems again. And then you can see is that here there is a bicycle, for example, coming soon, and it will detect before it is visible. I think it already went away. So if you look at this bicycle which was coming, it already started detecting, and then it comes, it appears later. So this is, I think, even one of the videos from my country because you can see there are 2 guys driving the bicycles and stuff, motorcycle. So we are trying to even extend those algorithms. So that's the research of the algorithm which I am doing to improve the efficiency of those algorithms and robustness, but also the portability on the mobile devices. Then we will hopefully release this as an app anybody can download and use in those countries, So, and it's for free, so they don't need to bother much about that. This is so one thing that we studied, that we I think the first 4 or 5 years we heavily worked on the public data sets and the stuff, but when we are subjecting them to the real world environments, unfortunately we see a lot of issues, and that's the robustness issues. A lot of machine learning algorithms do not function as well as this. So now at NYU AD I started tapping into the actual real world prototypes. So we, for example, this is a slam going on. So this Boston Spot, for example, is now doing a slam through this area. So this is a shared facility kinesis for multiple professors that we can use for our research. This is like a research platform for me, but I also got a dedicated lab space where I want to do a research with coordinated autonomous systems, which means that if heterogeneous of these things, like so there is a one Spot, one Husky, one row and one drone, and they are doing something collectively, how they will be working there. So this free area that you see here with the boxes, packed one, this is like the another part of the lab that I am developing at the moment. So this is like already you can see is a warehouse like stuff. This is a basement of our building. So the other one is like a shared facility where we can, let's say I develop an algorithm, I quickly go to that postdoc engineer and then he will port it on this device and then we'll start testing against that. So for example, here we are doing a slam using the Valadinos, this this 3D lidar. Now a couple of my students are working on the camera based visual slams algorithms, and the benefit of that is that they are very low cost and you can put them on a very small systems. So we are going to compare them against, for example, in this thing and stuff like that. So I skip this thing. So this is like a slam that we have done for the using the Husky, and this is also completely autonomous. So this is another work that we recently did. This is a neural slam algorithm going on. It's partly still doing the pose detection kind of stuff. We are extending it now, doing the depth estimation, and then see that how this will work. So I'll skip through that, so that you can see that this is the slam, that the map that we have built and the localization. So closing slide before we can talk the project later on, but at least the closing of the technical part. Most of these things that I've shown you are primarily the systems which are trained one time. Okay, like you have a big data set, you train them, you deploy them, done. But now if there is some new class coming which was not part of your training data set, your system will not function. Am I right? If you are subjecting your autonomous system in any unpredictable scenario, real world, which it has not seen in the training time, then you are gone. Now people are targeting this problem, but how? By recording the data, sending it to cloud again, doing the model update, and then doing this thing. But there is a big large scale initiative by DARPA, there is by NSF and also other organizations, which is called lifelong learning or real time learning or continual learning. So many different names for this, and you can go and look at the YouTube videos of Siegelman Hawa. For example, she is the program manager of DARPA, lifelong learning, and she gives a very nice overview of the challenges and problems. So that's one of the pictures from the ACM communication articles from them, where we just show that if you are going to design such kind of system for real-time learning or lifelong learning, the challenges are very, very different. I mean, imagine that now you have to do the training on the device. First of all, what should be your memory window on which you will train? How do you ensure that you are not forgetting what you learned previously? So all those kind of challenges are there. So there are like 5 or 6 biological learning properties that you have to fulfill. So I have an excellent student working in New York, with me, doing his PhD exactly on this topic. And then now currently, if you just think about that, we already talked about security issues. Now the security space for that is very, very big. Testing and verification of these algorithms is again a complex problem. So I think lifelong learning opens up a complete new set of problems for all of us, working in different areas of computer science, computer engineering, electrical engineering. This is like, all the problems and solutions have to be rethought when you're thinking about this. Now think this in a collective fashion. For example, there are 10 autonomous bodies learning together. Federated learning is one framework, but there can be other things also, So how do you handle those challenges there? How do you trust, those kind of stuff there? So this is again another great area. So that's the area where we want to move forward in the next couple of years. And the statement from the program manager is that in a few years, much of what we consider AI today won't be considered AI without lifelong learning. So that's another level of smartness. So I'll recommend you look at the IBM's roadmap for cognitive computing, where they start from smart to intelligent to all the way up to cognitive. So if system has to be cognitive, what do you do there? So that's the end from my talk. Some of the stuff, pictures I'm showing you of my team members to acknowledge them, that these are the guys. I'm the one who's standing and talking there. But these are the guys who have done the work. A lot of students, from our ECU lab, you can also see them here. A lot of students from my Vienna lab and some of the students in the Abu Dhabi's lab. So this is mostly the Abu Dhabi lab students. The upper row also, the middle one is there. Then you can see that these are my previous postdocs and stuff. These are most of the students that I have across 3 main campuses. I have a big project also in NUST going on. I have, you know, a lot of collaboration with Mauricio and Guido, and then also students, you know, things. So I'm also very thankful to my collaborators. There's a lot of knowledge that we have developed is, you know, with these resources, as well as the different educational system train you in a different way. I think a lot of what we have achieved is because of that, you know, that persons with different expertise, when they come together, they develop things which are not possible when you're developing at a single isolated location or not. And I think this is a great outcome in general. So summarizing, artificial intelligence has proliferated almost everywhere, and that's for a good reason. We require, you know, extremely energy efficient, secure and robust systems. I believe that we need a system level approach where you need a knowledge from all the abstraction layers. You need to know the ML algorithms very good so that you can design application specific systems, as well as you need to design those applications with consideration of underlying hardware, because now there is no hardware agnostic development anymore. We are moving towards a specialized era. If you look at the robomorphic computing initiative in US, you will see that they are talking about designing a dedicated chip for every type of robot which is deployed in this thing. This is another extreme of specialization which is coming in future for these robots, because you cannot get energy efficiency of that limit with just a general processor or anything like that. So specialization is the key, and we need to bring all these people together. So thank you very much for now. I have thesis topic. I will give it to you, I guess. You can present it later, am I right? Or we can talk about that later. So I have prepared a lot of interesting thesis topics, you know, where people can work with. But for the technical talk, I'm done now. So I'm happy to have your questions now. And once the recording is over, then we can talk about thesis topic in a much more informal, you know, setting. So thank you very much.